has an altitude that is also a median. Right, so remember, an altitude goes from a vertex to the opposite side and is perpendicular to that opposite side. And the median goes from the vertex to the midpoint of the opposite side. So when you start looking at these, if I draw in an altitude for that, it's not going to go to the midpoint. To go to the midpoint, it's going to go over there. So those are not the same. Right? And then for the next one, we have an altitude looks something like that, but the median would go to the midpoint there, so that doesn't match up. B, straight across, be an altitude, and it's also right there in the middle, which if you notice, you got two angles that are the same, making that an isosceles triangle, so it would make sense that that would split it perfectly in half. So B would be our answer there. And number 17, given segment AB and segment CD intersect at point E and angle 1 is congruent to angle 2. After looking at this question, it actually shouldn't be on this test because it's a similarity, not a congruence problem. But look at everything they gave us. You got 1 and 2 are congruent. And then 3 and 4, since those are vertical angles, those will be congruent also, which we can't prove any sides are congruent. All we got is those two angles, which, since this should be similarity, you can prove two triangles are similar with the angle-angle similarity postulate, but I said this shouldn't be on this test, so don't have to worry about it. Number 18, what's the area in square inches of the triangle below? So, area of a triangle, 1/2 the base times the height. We've got a base of 10, and the height off of that altitude right there is what we don't know. So we got to figure that out before we can calculate the area. So since this is an equilateral triangle, this altitude should split it perfectly, split the base perfectly in half, which allows us to know that that's 5 and 5. And since that's a right triangle, we've got the hypotenuse and one leg, so we can use Pythagoreans. A squared plus b squared equals c squared. So 5 squared plus the other leg, b squared, is going to equal the hypotenuse, 10 squared. So 25 plus b squared equals 100. Subtract 25. We get b squared equals 75. And then to get rid of the square, we take the square root. And 75 would break down to 25 times 3, and 25 as a square root, which is 5. So we end up with 5 square roots of 3. And so that's our height, 5 square roots of 3. And now we can use the formula. Area is going to equal 1/2 the base, which is 10, times the height, 5 square roots of 3. 1/2 times 10 is going to be 5, and 5 times 5 square roots of 3 is 25 square roots of 3. And 19, triangle PQR is an isosceles triangle. So since it's an isosceles triangle, we got two congruent sides, and we should also know that if it's isosceles, then the angles opposite those congruent sides are going to be congruent also. So if angle P is 3x plus 9, then angle R is also 3x plus 9. So now we've got a value for all three angles, and we know all three angles should add up to 180, so we can do 3x plus 9 plus 3x plus 9 plus 72 is going to equal 180. It's just a matter of solving for x from here. 3x plus 3x, 6x. 9 plus 9 is 18, plus 72 is 90. equals 180. Subtract the 90. And 6x equals 90. So the last step is to divide by the 6. So our x is going to be 15, which is B. All right, 20, John wants to make a triangular garden. Which of the following are possible dimensions? So remember the rule that any two sides added together have to be greater than the third side if we're going to make a triangle. So if we look at the first one, we got 4 plus 5, which would be 9, which would be less than 10, so that one can't make a triangle. 6 plus 6 is going to be 12, which is the same as the other side, which it's not greater than, so that can't make a triangle. 6 plus 8 would be 14, which is greater than 10, so that one will actually make a triangle. And 21, triangle ABC is an equilateral triangle with side lengths of 10 inches. So it's equilateral, so every side is 10. And really, if you look at this, this is the exact same triangle as what we used right here. And we're trying to find the altitude of it, which we already figured out here, so no reason to do it again. It's just 5 square roots of 3. Right. 22, in the triangle shown, GR is 11, BR is 8, and BG is 7. Which statement is true about the angles of RGB? So, what you got to keep in mind is that the angles and the sides are tied together, where the shortest side is across from the smallest angle, and the longest side is across from the biggest angle. And so if we look here, 7 is the smallest side, it's across from R, so that makes R the smallest or the least angle. 11 is across from B, 11 is the biggest side, so B would be the greatest angle, and then G is just going to be the middle one. Right? It's 8 is right there in between 7 and 11. So if we look at our possibilities, R is the least. That's actually C, which is a possibility. We know it's not the greatest, and G is in the middle, so it's not greatest or least. Alright, 23, Mr. Ammons is constructing a walkway through his rectangular garden. The walkway runs diagonally as shown in the diagram. Which is the closest link to the walkway? So since it's rectangular, we know these are right angles here. And the sides across are going to be the same, so this is 24, so that would be 24. 15 over here, so this is 15. And we're trying to find the length of this diagonal, so when we look at one of these triangles, it's a right triangle, and we're trying to find the hypotenuse. So once again, we would use Pythagoreans. A squared plus B squared equals C squared. So we got 15 squared plus 24 squared equals C squared. So 15 squared is going to be 225. 24 squared is going to be 576. Add those two together. 225 plus 576 is going to be 801 equals the C squared. And then to find C, we take the square root of both sides. And square root of 801 is going to be 28.302, which makes B the right answer at 28.3. All right, 24. While doing a research project about Vista City, Javier found the piece of an old city planner's map shown below. If all roads represented on the map are straight, what can Javier conclude about parallelism of the avenues and streets shown? So, if we look at the angles trying to find if they're parallel or not. We're looking for those relationships with alternate interior, alternate exterior, consecutive interior, or corresponding angles. Which right now, none of the angles that we have fit into a relationship, but if we find their linear pairs, so 135, this angle here is going to be 180 minus 135, which is 45. And if this is 45, then that's going to be 135 there. And if this one's 50, then 180 minus 50 is going to be 130. So we're looking for angles on the transversal that match up. And if I look this way, we got 135 and 130 that are corresponding angles, not the same, so that means that the streets are not parallel. And then when we look this way, on this transversal, the top one, we got 135 and 135, which are corresponding angles, and they're the same, and 45 and 45 corresponding angles that are the same. So from there, we know that these two lines are parallel and these two lines are not. So the avenues are parallel, but the streets are not. That would be A. 25. Which of the following segment lengths can be used to form a triangle? So once again, checking to see which two add up together to be greater than the third side. So 2 plus 3 is 5, which is the same as 5. So it's not that one. 2 plus 3 is 5, which is definitely less than 13. So that one doesn't work. 2 plus 4 is 6, which is less than 7. And 2 plus 5 is 7, which is greater than 6. So that would be our answer there. 26. Right triangle's hypotenuse has a length of 5. If one leg has a length of 2, what's the length of the other leg? So we got a hypotenuse of 5, a leg of 2, and we're trying to find the third leg. So once again, into Pythagoreans. So 2 squared plus b squared is going to equal 5 squared, or 4 plus b squared equals 25. Move the 4 over, subtracting it. So b squared is 21. And so to find the square root of both sides, end up with b is the square root of 21, which matches up with b. 27. Two angles of a triangle have measures of 55 and 65 degrees. Which of the following could not be a measure of an exterior angle of the triangle? So if I've got a triangle here with 55-degree angle and a 65-degree angle, we need to know what the third angle is. So we're going to take the 180 and subtract 55 and 65. Which 65 and 65, 55 and 65 together is 120. So 180 minus 120 is 60. That gives me my third angle. And now we want to look at the exterior angles. So if we extend one of the sides at each vertex, see we've got a linear pair. So for the top, we got 180 minus 60. Because those two angles together have to add up to 180, and so got 120 for that exterior angle. Here we got 65, so 180 minus 65 is going to be 115 for that exterior angle. And then 180 minus 55 will give us 125 for that angle. So we got 115, 120, 125, but we do not have 130 as a possibility. All right. 28. Which collection of segment lengths could not be the lengths of the sides of a triangle? So in this case, it wants to know which one could not be the length of the side of a triangle. So we're looking for one that doesn't work. So 1 plus 2 would be 3, which is the same as 3, not greater than. So A should work for our answer. We can go ahead and make sure the rest of them. 1 plus 3 is 4, which is greater than 3, so that one would actually be a triangle. So that one isn't the answer. 2 plus 3 is 5, greater than 3. That's not the answer. 2 plus 3 greater than 4. So it is the only one that could not be a triangle. All right, 29. Looking at this figure here, we want to figure out which triangles must be isosceles. So if I start up here at the top, we've got a 90-degree angle here, 46, and then we don't know what this angle down here is. And they don't give us much of any information to go off of the sides, but if you got an isosceles triangle, it does have 2 congruent sides, but then it should also have 2 congruent angles opposite those sides. So we got to focus on the angles here because that's really all the information they gave us as far as numbers go is on the angles. So if I look at triangle TUQ, I've got a 90-degree angle here, so that means that these 2 acute angles here should add up to 90. So if I take 90 and subtract 46, it's going to give me 44. So I've got 2 different angles. They're close, 44 and 46, but they're not the same. So TUQ is not an isosceles triangle. And if we come down here to this triangle with the 68-degree angle at V, we don't have another number given to us, but we should recognize that we got an intersection of 2 lines here. So this is a vertical angle with this angle right here, and those should be the same because they're vertical angles. So if this one's 44, this one's 44, and then we can use that to find the third angle. So 180 minus 68 minus 44, which is going to be 180 minus 112, which is going to be 68 degrees. So that angle right there is 68 degrees, which matches up with this one. So you got 2 congruent angles making this triangle an isosceles triangle. So SQV, which is D, it's going to be isosceles. And then 30, we got points R and T that are the midpoints of the sides of the triangle QSU, as shown in the diagram below. So R and T are midpoints of these sides, which means that this segment here is a mid-segment. And we know that a mid-segment is half the length of the side of the triangle it's parallel to. So RT is parallel to QU. So RT should be half of QU, or half of 28. It's going to be 14. And then we notice we got congruence marks here and here. So this segment is congruent to segment QR. Segment QR is 14, so segment SR should be 14 as well. And then we got double congruence marks that match here and here at ST and UT. UT is 12, so ST should also be 12. And so now at this point we've got the measure for all 3 sides. Finding the perimeter is just adding the 3 sides together. So 14 plus 14 plus 12 will be 28 plus 12, which is 40. So the answer is B. And that concludes this review.